Now what we're doing is incorporating the relationship between one rate and another rate, right? It's going to involve us taking derivatives and antiderivatives, but using no new skills, all right? So we're done with the part of the course that requires you to learn a new process. So no new chain rules or anything like that. It's just applying stuff that you already know. So that's good news. And, you know, if you're weak in some of those areas, it gives you an opportunity to go back and strengthen yourself with them. Right? You'll see some of these steps in the process, they're pretty familiar. You've been taking math classes for a long time. You look at draw a diagram. Well, yeah, okay. You have a problem that requires you to visualize a situation, you draw a diagram. Right? I would include, if applicable, or if necessary, depending on which word I remember how to spell. I think I can handle applicable. I get a little jammed up on the 2 C's or 2 S's in necessary. I think it's 1 C and 2 S's, but I'm not 100% sure. Not confident enough to go for it. That's really where I'm at. Determine which quantities and rates are given and which are to be found. Identify the primary function to use. Often this is a formula from geometry. All right, we'll see what that looks like in a few minutes. Differentiate with respect to the independent variable. So differentiate, that's the calculus step, or at least for this type of related rates problem. That means derivative. Write a related rates equation. That's kind of like a throwaway step, maybe not, but let me just kind of explain. If you do steps 1 through 4 correctly, that'll give you step 5. All right. So it's not a unique equation that you would need to write. It is a consequence of steps 1 through 4. So if you do all that stuff, then step 5 should work itself out. Step 6 is algebra, or computation anyway. Plug and chug, get an answer. All right. The one thing I would throw into the mix here: interpret your answer in the context of the problem. All right. Now, you just got to be careful with context because, oftentimes we think we've stated something in context, but we haven't quite done so. And if you're talking about an object in motion and you get a derivative of -2, you might say the rate of change of the object is -2. That's not in context. The rate of change of the object is -2 meters per second. Also not in context. The object is falling at a rate of 2 meters per second. That's in context. All right, so you're telling me what's happening to the object over time. All right, so you're addressing the numerical value, the units, and also the sign of the numerical value. All right, so those are some key ingredients. Very easy to lose sight of, but generally speaking, if you're talking in generalities, you're not doing your job. All right, so that's supposed to be hilarious. So example 1, air is being blown into a sphere at the rate of 6 cubic inches per minute. How fast is the radius changing when the radius of the sphere is 2 inches? You start off with an easy one. It may not seem easy because this is a pretty crunchy topic, but just analyze the situation unit by unit. Cubic inches per minute. I'm going to rewrite that. All right. Now forget about the numbers for a second. How fast is the radius changing when the radius of the sphere is equal to 2 inches? All right. So they're asking me a question about the rate of change of radius. I'll get to that. But they give us a measure in terms of inches. All right. So let's tackle the inches cubed per minute. Look at that. All right, inches cubed is a measure of what? Volume. All right, distance cubed, all right, 3 dimensions gives us volume. All right, minutes, that's easy enough, right? Time. Now, in saying that the air is being blown into the sphere at that rate, is that rate over an interval or is that an instantaneous rate? What does it seem like anyway?
Interval.
Interval, possibly. But if you think about it, they didn't really give us an interval of time, so there's no way for us to tell. We would have to assume that this means that at any given moment, the rate of change is that number, right? So does that change your thinking?
Yeah.
Yeah, so we're looking at instantaneous. All right, so using proper notation, how could I represent the instantaneous change in volume per unit of time? dV dt. All right, the units told the whole story there. Or at least it told most of the story. It gave us a rate of change. It was just a question of, is it an average rate of change or an instantaneous rate of change? All right, so that's really what we're after here. So they're asking us how fast is the radius changing, all right? So how fast is the radius changing? Let me write that down. How fast is radius changing under what circumstances? Radius changing, well, the volume is changing per unit of time. Does it make sense that the radius would also be changing per unit of time? Yeah. So per unit of time. All right. Would that be on an instant level also? Yes. Probably. So that's asking us for a dr dt. All right. So we have a dv dt. We need a dr dt. This inches measure, well, they told us flat out that that's radius. All right. So we know that the inches represents radius. I can make a little note of that. Let me go purple for those keeping score at home. So that would be my R. All right, so what I need, specifically related to a sphere, is a formula that relates volume and radius for a sphere. Do we know what that is?
4/3 pi r cubed.
Exactamundo. All right, so volume of a sphere is equal to 4/3 pi r cubed. All right, now I said I need a formula that relates volume and radius, but that's kind of misleading you a little bit. What I really need is a formula that relates dv dt and dr dt, but I didn't think it made sense to start with that. All right, because if I have this equation, I can take its derivative and get these values. All right. The issue is we have to take the derivative using implicit differentiation. Right, so that's way back in December. All right, so I'm going to take the derivative of this with respect to time. So dv dt would be equal to, what would the derivative of 4/3 pi r cubed be equal to? 4 pi r squared, but by the chain rule, we have to assume that the r could be variable. So the chain rule always tells us to take the derivative of the inner function. What would the derivative of r be? dr dt. All right, that goes back to implicit differentiation where we were saying that if we're taking the derivative with respect to a variable that is not the same as the original variable, you just slap on a d whatever dt at the end, or d, at that time it was d whatever dx.
I move up because this desk is just driving me crazy.
Yeah, sure.
So the R, like, basically that's allowing for the R value to change?
Exactly.
Okay.
We can't assume that the r is a constant. It could be a variable function.
So you said the original variable, so that's b? Like, that's why it's just r, and then r is dr over dt,
Because we're taking the derivative with respect to t rather than v or r. Correct. Correct. Sorry, my shoelace, I'm untied. I gotta lock it down. It's the first time I had to do that in like 6 months. It's crazy. All right, so I have this related rates equation. All right, now all these notes you wouldn't have to write. Dang it, I'm in a jam now. My left shoe is tighter than my right shoe, and now my equilibrium's all thrown off. Sorry, I just got to do it. Got to bring it back into equilibrium. Now the slip-on, slip-off aspect of the sneakers is going to be compromised. It's a little bit better. All right, anyway, what we have here is our related rates equation. Right? Now, do you really have to consider all of this stuff every single time you solve a problem like this? No, because when you take the derivative, you're really just taking the derivative as you normally would and just slapping on a d whatever dt. So the derivative of v would normally be 1 multiplied by dv dt. Derivative of r would normally be 1, so dr dt. Right? You'll see it in action a little bit more in a couple of minutes, but it's not as challenging as it might seem, at least to carry out the process. It's incredibly challenging to understand why all this stuff works the way it does. Right? That's why you have to wait all these years to take a course on calculus, because you have to have all the fundamentals in place. But for now, we can get the process down and worry about the whys later on. But it is rooted in chain rule, which is kind of cool. All right. So the volume is increasing at a rate of 6 cubic inches per minute. So they gave us our dVdt is equal to 6. 4 pi. They tell us our radius is 2 squared. I'm looking for dRdt, so I don't have a variable for that. Now it's just basic algebra. Stay away from decimals unless the question asks you to work with decimals. You don't want to get into that. I'll even take your fractions in unsimplified form if you want, but don't give me anything ridiculous like 25 over 50 as a final answer. Like that you can reduce down to 1/2. I've even had people give me 100 over 50 and wonder why I take off half a point. Hey, I'm not doing it because you're incorrect. I'm doing it because you insulted me by writing 100 over 50. Like, no, write the 2. So that was a weird conversation, though. That actually happened. I'm like, you're like, why'd you take off for me writing 100 over 50? And I'm like, why did you write 100 over 50 instead of 2? You said we didn't have to simplify. Yeah, but it's 100 over 50. Like, you couldn't make that a 2? Hey, come on. Now imagine that exchange going back and forth for a good 10 to 15 minutes of class time. So, anyway, 16 pi is what this would become. So 6 over 16 pi. That's not quite the same as something like 10 over 20. So if you left it like that, I'm not losing any sleep. But obviously the better answer is 3 over 8 pi. It's an attempt at drawing a 6, yeah. Units? Inches per minute. All right. So inches per minute is an important part of it, or at least the units. We know it's dRdt. The derivative itself, the way the notation is represented, tells you exactly how you should represent your units. dr is the rate of change of r. All right? R is represented in inches. So there's your inches. dt is related to time. Time is measured in minutes. So you're actually just taking the rate of change of inches and minutes. So it comes right from this notation. All right? So will you be losing credit if you don't include the units? Yeah, you're going to lose credit if you don't include the units. All right, it's the most important part of this. All right, the numerical stuff is important, but understanding how the units tie in is equally as important. That being said, you might have noticed on the board that we're still in the possible stage here, possible unit test at the end of the unit. which I guess is the definition of a unit test. I don't know yet, and it has nothing to do with you all. It has to do with me being able to put together a nice activity along the lines of what we did yesterday. Right? I have some ideas in mind. I just haven't been able to get them to work. You know, it's kind of like if I were a science teacher and I had this great idea for a lab, but the lab never works when I try it out, then I can't ask my students to do it. You know, there wouldn't be any conclusions. So I'm like this close to getting it to work. So if that happens, then it'll be great. There won't be a test. But if I can't get it to work, then unfortunately there'll have to be a test. So you want to be rooting for me on this, basically.
Unit test would it be group or individual?
It would be individual. Yeah.
Yikes.
So you're really rooting for me, like really.
Class support just like skyrocketed.
Yeah, just good moral support, positive energy. That's all we're looking for. Honestly, I feel like. Well, what I need is an avocado, a lengthy piece of string, and
An arm.
Human arm.
and a human arm. No,
I think I've got that in my backpack.
actually,
I was thinking more like a robot arm, but okay, that.
let me think. Well, I guess I could talk about it because. Anyway, the edge of a cube is increasing at a rate of 2 inches per minute. All right, so let's think units here. 2 inches per minute. So that's a linear measurement divided by a unit of time. All right? They're telling us, and we'll get into what that represents in a second. At the instant the edge is 3 inches, how fast is the volume increasing? Well, the good news is, how fast is the volume increasing? Well, we just kind of addressed that. We know now that that's going to be dV/dt. All right, the edge of a cube, well, we can call that a side. Do we have a formula that relates?
Wait,
The-
DVDV?
Oh, my bad.
Typo point. Just joke. It was a joke, guys.
I assumed it was a joke based on the woo at the end. Yeah, like that. So anyway, do we have a formula that relates volume and the length of a side of a cube?
Side square.
Side cubed. All right. So what we would do is let that 3 represent the length of the side. We call that S. All right. Which means that the inches are taking on the role of a side. So rate of change of side per unit of time. All right. So we have a formula that relates volume and the length of the side. I need one that relates the rate of change of volume with the rate of change of a side. So what do I do? Do calculus. Yeah, exactly. What kind of calculus? We learned basically 2 kinds. Differentiation, exactly. So dV/dt would be equal to what? I got that, yep. What's the other part? The SDT, yep. Alright, so we're always just multiplying by the derivative of what the inner function is. And again, it's very misleading because that S does not look like it would be a function, but you have to assume that the length of the side could change at a variable rate, in which case it's its own function. S as some function of t. Alright, so maybe S is t squared minus 32t. Maybe S is just 2, but we don't know, so we have to account for that. Right? If it turns out it's constant, then ds dt will just be equal to 0. But again, we can't make that assumption. All right, so we know that the edge is increasing at 2 inches per minute, so that makes ds dt equal to 2. S is given as 3, and we just need dV/dt.
Can you just plug it in there?
Just plug it in. All right, you don't want to plug in any numerical values until after you've taken your derivative, because if you do, let's say I plugged in the 3 for S before I took the derivative, what's going to happen? What's 3 cubed? 27. What's the derivative of 27? 0. It makes us think that the volume is not going to change. Is that true? You increase the length of a side of a cube, does it not get bigger? It gets bigger. So it's going to contain more volume. Right? So to come away with a 0, that would be a problem. Right? In this case, we're looking at 54, what are my units?
Inches cubed per minute.
Inches cubed per minute. And that's our rate of change of volume.
Okay.